Welcome back. In this video, we're going to continue our discussion of discrete probability distributions, and we're going to focus a little bit on a different type of distribution. In the previous videos, we've been dealing with, binomial type patterns, a true or false problem, or, a hypergeometric, which was our classic pool problems. In this one, we're dealing with the Poisson distribution, which is more of a pulse problems. And this one's very useful in things like queuing theory and, arrival departure studies, at restaurants or airports or anything like that. And so that's the way we're going to look at this one. All right, so the Poisson process basically is the probability of an event when it is proportional to some sort of time interval. So there's going to be a rate factor that's going to be a major issue. Now, books write it different ways. I've historically always written it as lambda. The Devore text will write it as this mu value, if you will. And I don't like this one because classically this is also the same character that's used for the population mean. And that's just, there's some confusion that can happen. So for us, I'm going to end up dealing with just with a lambda pattern. But I'll point out that in the tables in the book, they actually use that micro symbol. So, or mu. So, all right. So the way that you identify a Poisson problem is it's always dealing with pulses or arrivals of people, of planes, of events happening. All right. And so the basic definition says that the probability of our random variable x being equal to some value, which is always this little x, we're going to write it as it's a Poisson distribution, and it has two parameters. It has x and then lambda. I have to know both. And the basic formulation for this process is e to the minus lambda times lambda raised to the x power all over x factorial. Okay, and where x is equal to 0, 1, 2, or any positive value. Okay, and also that lambda is always greater than 0, that it's a rate type of problem, all right? When we define this process, the expected value and the variance both take on the characteristic of this rate parameter, this lambda value. So it's very, very easy. You'll always know the expected value of a Poisson problem, okay? Because you always know the rate on which you're doing your study. Okay. All right. So now, if you notice, the Poisson distribution, while we said it was different, it does have its roots in the binomial. Okay, so if we remember, a binomial required an x, an n, and a p. Okay, when n gets very large and our probability p gets very small, this guy tends towards a Poisson distribution type of response. Okay, so they are the Poisson's kind of a special case of the binomial. And in that Poisson distribution, then lambda is equal to n times p. And if you remember from the binomial, this n times p value was also the expected value for the binomial distribution. So that's where this is coming from. Okay, it does have its relations there, though we don't often think of it in that way, and we do use it a little bit differently. All right. Okay. So what we can do is we can kind of rewrite this a little bit, such that we have the probability of x events occurring during a time t then is taken as the probability of x being equal to that value again with a parameter of t. Then all I have to do is kind of rewrite things a little bit. And so it's e to the minus alpha times t, okay, times alpha times t raised to the x. So again, all we've done is we've kind of recast this lambda thing. Okay, that's our Poisson PMF. Okay, and in this, lambda is equal to alpha times t. Okay, where alpha, which, obviously we can rewrite it, is basically the rate of occurrence. It's, 5 customers come into the store per hour, or, 2 planes depart every 20 minutes, those kind of things. And so that's what alpha is. Okay, now the thing that we have to watch out for is you got to watch the units on alpha. If it's in something per hour, then the time characteristic goes in needs to be in hours. Okay, if it's in minutes, this needs to be in minutes. There has to be some sort of correlation or matching of what's happening on those. So that's our basic Poisson process. So let's try one. Okay, so we got kind of an aircraft arrival problem on this one. And in this, okay, we have the fact that aircraft arrive at a rate of 8 planes per hour. Okay, so again, the tip off to this is that time value. So we're doing 8 planes per hour, that's your alpha. Okay, so we know lambda is equal to alpha times t. Okay, Again, we have to have the same characteristic of time. Okay, so we got to make sure our time units match. You might have to do a units conversion on one or both of these. Okay, and so then the Poisson distribution for this example is going to be probability of x being equal to whatever value I'm looking for in a parameter of t is going to be e to the minus 8t multiplied by 8t all raised to the x power, and then all that divided by x factorial. All right, that's it. That's all there is to it. So that's our basic equation as we start to kind of lay this thing out. All right, so let's figure out, what's the probability that exactly 6 will arrive in 1 hour. And I left off the word arrive there. Okay, will arrive in a 1 hour increment. Okay, now it could be 0 arrive, or technically, theoretically, according to this distribution, it's possible you could have an infinite number of planes arrive in a single hour. Now, probability will be very, very small, but it is there. But for us, we're going to choose 6. Seems like a reasonable number given a rate of 8. Okay, so probability that x is equal to 8. We're going to plug in this. Okay, and again, what's happened here is we also have the 1 hour factor that goes in there. And so in our formula, if you look back up on this, I'm plugging in 1 hour for t. So t is equal to 1 hour on this there. Okay, and so it's just a math problem. So e to the minus 8 times 8 raised to the 6, and then all over 6 factorial. And so we can say that based off of this distribution, we would have a probability of 0.122 for 6 arriving in 1 hour. Okay, and again, as this number gets bigger, that one goes down. Okay, and then it kind of, this is a skewed distribution, if you will. It's very, left skewed more towards the lower numbers than it is toward the higher ones. Okay, so now we can also do kind of some other skills that we've learned in other videos. Probability that at least 6, so again, we've got a keyword here, and that at least 6 arrive in an hour. That's just simply it's 1 minus the probability of at most 5 for us there. Okay, so we can flip it, and this was a complement, so at least 6, the complement of that is at most 5. And so I write that as probability of x greater than 6. Again, t is 1 hour on here is equal to 1 minus the probability of x being less than or equal to 5. Well, if you remember from our basic discrete random variable discussion, this becomes a cumulative distribution function. And if you've got questions on where this is coming from, go back and try looking at the video for that a couple of videos back. Okay, and that'll help clarify some of these terms. But CDF stands for cumulative distribution function, and that's our basic definition. And so for a Poisson, then it's simply 1 minus, and then this cumulative, I could do it a couple of different ways. I could do it the brute force method, where I just sum up all of the possible values of x that satisfy this. So it would be x equals 0 and x equals 1 and 2 and 3 and 4 and 5. Okay, and then I run that equation for every one of those. So then that's what I've done. I've done a summation notation here, where I'm summing from k equals 0 to 5, and then of e to the minus 8, 8 to the k, and then k factorial. So I have to do some math. And like I say, for a couple, it's not a problem. But if you're doing 1,000 of these, this gets a little annoying and a little irritating to do. The math on this, and I didn't write all this out, but the math on this proves that this number is 0.191 for anything less than 5. Okay, and so 1 minus that number gives me a probability of 0.809. Okay, now I am going to point out that your textbook and a lot of resources will have cumulative distribution tables. So I'm going to pause the video real quick and pull up the book. All right, so in this, what I've done is I've pulled up in the DeVore textbook and gone into the back in the appendix in table 8.2. Okay, you can see this is a cumulative Poisson distribution for us. And you can tell that it's cumulative, not only because of the title, but just because of the way they write this thing. That they're going a capital F. And if you look at the parameters, it's x and it's mu. Okay, the mu in this table, that's the lambda parameter. Because if you look at the formula, you can see that it's the formula that I've showed you already, where they're summing y equals 0 to x, and then e to the minus mu, mu to the x all over, or sorry, mu to the y, and then all over y factorial on this. So mu is clearly lambda in our definition. So if you want to, in your book, just pencil this out and call that lambda, that's fine. But the way the table's set up is very, very easy, is that you have different lambda values or different rate parameters on this. Again, this guy is a unitless quantity, okay, and so, but they give you for specific guys a 2, 3, 4, all the way out, 8, 15, and goes up to 20. So you're kind of limited on the ones that it gives you, but it becomes very, very easy. So for our example, where we were looking for, for x less than or equal to 5, we would come down on this column. This is our x column. It's kind of off the edge of the paper. You can see there's x on there. Okay, and so I would basically read down. We had a rate parameter of 8 per hour, so that's lambda is 8, and I would read down to 5, and so I'm going to basically read across to 8 at 5, and there's my 0.191. Okay, so it's the exact same number that you had before. And so these tables are very, very handy for that kind of thing. And I'm sure that MATLAB has a function that will generate these numbers for you if you want, or it's very easy to program this into Excel as a macro or a spreadsheet or something to help you out with that. So the cumulatives, again, are very, very handy if I can get a problem set up. So I'm looking for x less than or equal to some value. Okay, all right. So with that being said, we'll put that away. Okay, the Poisson cumulative is very, very easy, and you'll notice that in a lot of the discrete problems, and even in some of the continuous probability distributions, there will be tables that we can make use of that will simplify our math. Okay, and so just kind of what we showed on this, and we could do another one. Probability of x greater than or equal to 10 is equal to 1 minus probability of x less than or equal to 9. Again, you've got to kind of watch the direction. That if I can flip it this way, now it becomes a cumulative. And then for us, if we had looked up in the table, you would have found that value was 0.717. Okay, and so 1 minus that number then gets me the 0.283. And that's the way it kind of works as a cumulative function. All right, okay, so that's our process there. Okay, now the next question that we can ask then is, what's the expected number of arrivals and the standard deviation for 1.5 hours? Okay, now we said that the expected value of x was equal to lambda. Okay, and we still have 8 planes arriving per hour. Okay, but remember that the 8 per hour on this was equal to alpha. Okay, and so the expected value then for a 1.5 hour period then is going to be 1.5 times that number. Okay, so lambda is always alpha times t. So you're always, for every scenario, you have to come back and reevaluate lambda, because this can change from one problem to the next based on how that time factor changes. All right, so our lambda, which is our expected value, is going to be 8 arrivals per hour times 1.5 hours. We now have 12. So your lambda has changed from 8 in the last problem to now 12 in this. Okay, so lambda is equal to 12 arrivals, and we know that the variance is the same value, is 12, and so sigma is the square root of 12, and so this is 3.464. And so you have the statistical points that you need for the mean and for the standard deviation. But remember, the probability of x being equal to x, given that my lambda is now 12, okay, this is going to be equal to e to the minus 8t times 8t all raised to the x, okay, all over x factorial. That's still our distribution. But when I rewrite this with t equal to 12 on there, this is now e to the minus 12 times 12 to the x all over x factorial. So your equation has changed a little bit as we start to kind of work that. So it's the same basic form. I plug in my t of 1.5 hours now, or I can rewrite the entire distribution. You can see how it changes based off of the time. So it's a little bit different. Okay. So then you can come in, well, what's the probability that at least 20 arrive during a 2.5 hour period? Okay, so we would write that probability of x greater than or equal to 20. My time is 2.5 hours. Okay, and so we're looking at keywords. At least tells me, all right, I want to flip this to make it a CDF. So we're going to look at the 1 minus the probability that x is less than or equal to 19, t is equal to 2.5. Okay, and so the first thing we got to do is we got to go find our lambda. Okay, that's alpha times t. That's 8 arrivals per hour multiplied by 2.5. Put some units on there. Hours was going to give me 20 will be my lambda now for this study. Okay, so if we go from table 8.2 back in that table, and we were to look this value up, we would choose a lambda of 20 and x of 19. Okay, and you should find a value of 0.470 as your probability that comes out of that table. All right. And so if we do that, then the answer to the question that I'm asking is probability that x is greater than or equal to 20, okay, for a t of 2.5 hours is just simply 1 minus 0.47 or 0.53. Okay, all right, so to kind of recap, and I know this is a shorter video, but I just kind of wanted to talk about the Poisson distribution by itself because it is a little bit of a different animal, is that we're going to note that the Poisson events are basically the number of pulses in a given time. So there's always a time factor, and there's always, we say pulses, but that's a rate, okay, for a given time. Okay, and then of course there's always, if you remember, if you're watching for keywords in this, looking for at least or not more than. Okay, if you see either one of those, use a complement and the CDF tables, and these problems become very, very easy. Okay, so anyway, that was fairly quick. I hope it made sense to you. As always, toss us a like on the video if it helps you out at all, and leave us some feedback or some comments if you have any questions on this, and we'll try to get back to you on the comments on those. And as always, subscribe to the channel. So anyway, have a great morning, and we will see you guys next time. Happy engineering.